The year is 1950. The world is on the brink of a technological revolution. The streets are bustling with people, cars, and the hum of industry. But behind the scenes, in quiet laboratories and universities, a new kind of revolution is taking shape. Alan Turing, a British mathematician, proposes a question that will forever change the world. Can machines think? This question isn't just a fleeting thought, it's a profound inquiry that challenges the very nature of intelligence and consciousness. This simple question ignites the field of artificial intelligence, or AI. Scientists and engineers begin to dream of machines that can mimic human thought processes, machines that can learn, reason, and even create. AI is the quest to create machines that can perform tasks that typically require human intelligence. These tasks are not just limited to calculations or data processing, they encompass a wide range of activities that we often take for granted. These tasks include things like learning, problem solving, and even creativity. Imagine a machine that can compose music, write poetry, or solve complex mathematical problems. The possibilities seem endless. Early AI research focused on logic and rule-based systems. Scientists believed that if they could just program enough rules into a computer, it could simulate human thought. Scientists tried to program computers with all the rules needed to solve problems. They used punch cards and early programming languages to input these rules, hoping to create a machine that could think. Imagine trying to explain how to ride a bike by writing down every single step. This approach had limitations. It quickly became apparent that some tasks were too complex to be broken down into simple rules. The real world is messy and unpredictable. No matter how many rules you write, there will always be exceptions, unexpected situations, and nuances that are difficult to capture. It's impossible to write a rule for every situation. This realization led to frustration and a sense of hitting a wall in early AI research. AI needed a new approach, one that could learn from experience. This was the dawn of machine learning, a paradigm shift that would eventually lead to the intelligent systems we see today. By allowing machines to learn from data rather than relying solely on pre-programmed rules, scientists opened the door to a new era of AI innovation. In the 1950s, a new idea emerged: Markov chains. Imagine a child learning to speak. They hear words and phrases repeated and they start to understand the patterns. Markov chains work in a similar way. They are mathematical models that learn patterns from sequences of data. They can predict the next item in a sequence, like the next word in a sentence. While simple, Markov chains were a major breakthrough. They showed that machines could learn from data, paving the way for more sophisticated generative models. Inspired by the human brain, scientists developed artificial neural networks. These networks are made up of interconnected nodes, or neurons, that process and transmit information. Just like our brains learn from experience, neural networks adjust their connections based on the data they receive. This ability to learn from data is what makes neural networks so powerful. However, early neural networks were limited by computing power and the availability of data. It wasn't until the 21st century that they truly began to flourish. Section 4. Learning from data, the rise of machine learning. With the rise of the internet, data became abundant. Every click, every search, every social media post generated a wealth of information. This data, once scattered and unstructured, began to be collected and stored in massive quantities. Companies and researchers realized that within this data lay hidden patterns and insights that could revolutionize industries. The challenge was how to make sense of it all. Computers became exponentially more powerful. Advances in hardware, such as GPUs and specialized processors, allowed for the rapid processing of vast amounts of data. This computational power was essential for running complex algorithms and models. The combination of abundant data and powerful computing created the perfect environment for machine learning to thrive. This perfect storm led to the explosion of machine learning. Researchers and engineers began developing algorithms that could learn from data, identify patterns, and make predictions. These algorithms were not just limited to academic research, they started being applied in real-world scenarios, from healthcare to finance, from marketing to autonomous vehicles. Machine learning is a type of AI that allows computers to learn without being explicitly programmed. Instead of writing code to solve a specific problem, developers create models that can learn from data. These models improve over time as they are exposed to more data, becoming more accurate and efficient. This approach has transformed how we solve problems and make decisions. It's like teaching a dog a new trick, not by giving it a list of instructions, but by rewarding it for doing the right thing. This method, known as reinforcement learning, is one of the many techniques used in machine learning. By providing feedback, the model learns to make better decisions over time, much like how a dog learns to perform a trick through positive reinforcement. Generative models are a subset of machine learning. These models don't just analyze data, they create new data. For example, a generative model can be trained on thousands of images and then generate entirely new images that have never been seen before. This capability has vast applications, from creating art to designing new products. They learn the underlying patterns in data and use that knowledge to create something new. This process involves understanding the structure and distribution of the data, which allows the model to generate realistic and coherent outputs. The ability to generate new content opens up exciting possibilities in various fields, including entertainment, design, and scientific research. Think of a musician learning different musical styles and then composing their own original music. Just as a musician draws inspiration from various genres and techniques, generative models draw from the data they are trained on to create something unique. This creative aspect of machine learning is pushing the boundaries of what technology can achieve, blending the lines between human creativity and artificial intelligence. Section 5, Two Sides of a Coin: Generative Adversarial Networks. In 2014, a revolutionary new type of generative model emerged, the Generative Adversarial Network, or GAN. This innovation was introduced by Ian Goodfellow and his colleagues, and it has since transformed the landscape of artificial intelligence and machine learning. Imagine two artists, one trying to forge a masterpiece and the other trying to detect the fake. This analogy perfectly encapsulates the dynamic between the two components of a GAN. A GAN consists of two neural networks, a generator and a discriminator. The generator's role is to create new data such as images, text, or even music, while the discriminator's job is to evaluate this data and determine whether it is real or generated. The generator creates new data, such as images or text, by learning from a training set of real data. It tries to mimic the patterns and structures it observes in the training data to produce convincing outputs. While the discriminator tries to distinguish between real and generated data, it acts as a critic, evaluating the generator's creations and providing feedback on their authenticity. This adversarial process pushes both networks to improve. The generator learns to create more realistic data to fool the discriminator, and the discriminator becomes more skilled at identifying fake data. The generator gets better at creating realistic data, which can be used in various applications such as image synthesis, data augmentation, and even art creation, while the discriminator becomes more adept at spotting fakes. This continuous loop of creation and evaluation leads to the generation of highly realistic data, pushing the boundaries of what artificial intelligence can achieve. Section 6 transforms the shape of language to come. Language is complex. It relies on context, nuance, and understanding of the world. Traditional neural networks struggled to capture these intricacies. Then came transformers. These models are particularly good at understanding the relationships between words in a sentence. Imagine reading a book and understanding how each sentence builds upon the previous one. Transformers revolutionized natural language processing. They power chatbots, language translation tools, and even creative writing assistants. Section 7, the age of creation. Generative AI today. Today, generative AI is everywhere. It creates stunningly realistic images, composes music, writes different kinds of creative content, and even designs new drugs. The possibilities are endless. Imagine a world where anyone can create a Hollywood-quality movie, compose a symphony, or design their dream home using AI tools. Generative AI is not just about creating art or entertainment. It has the potential to revolutionize every industry, from healthcare to education to manufacturing.